calculate phi and how we calculate omega. We calculate the relative humidity and the humidity ratio, and we can convert from one to the other. Next is to calculate the mixture enthalpy. Okay, so the mixture enthalpy, one weird thing that will happen in the mixture enthalpy is he's gonna calculate it. So what's the unit of the enthalpy? You usually would say it in kilojoule per kilogram, right? Kilojoule per kilogram. Energy per unit mass. And the mass would be the mass of the species that we are calculating it for. So if I tell you find the enthalpy of the water vapor at this temperature and pressure, piece of cake. You go to the steam table, you have the pressure and temperature, and you read the enthalpy, kilojoule per kilogram of water vapor. And the same thing for the air. There are tables for the airs, or in the easiest way ever, we can maybe even use CPT. The point is you will end up getting the enthalpy joule per kilogram of the air, right? Dry air. So now when you calculate the mixture enthalpy, you should expect the dimension or the unit will be joule per kilogram of mixture, right? Just like all of them. No, they don't. They do it joule per kilogram of dry air. And you'd say, but the mixture have also water vapor. They say, sure, but we wanna keep all the calculation per dry air. And you will see how this may complicate a little bit the first law of thermodynamics when we have our enthalpy joule per kilogram of dry air rather than joule of kilogram mixture. So the complication, you will find that we will end up calculating then everything per kilogram of dry air to make our life easier. So even if we would like to calculate how much heat is going into the duct, the HVAC duct, for example, from the heater, we will end up saying, well, how much heat per kilogram of dry air? And yes, there is not just dry air, there's also water vapor. But just to simplify our life, we will calculate everything per kilogram of dry air. All right? So let's start. Let's see how does this work. So over here you see this is the total enthalpy, the mixture enthalpy. And so the mixture enthalpy is the addition of the two components he got. He got some enthalpy in the air, dry air, and he got some enthalpy of the water vapor. And so that capital H, that's joule. The small h is joule per kilogram. So if you want to get the joule, you do the specific enthalpy, the joule per kilogram of dry air, multiply by the kilogram of dry air, right? So notice that the HA is the enthalpy of just the dry air per kilogram of dry air. And the H vapor, what is that HV? That is the enthalpy of water vapor per kilogram of water vapor. That's what you get from the steam table, right? Specific enthalpy multiplied by the mass of the water vapor, how many kilogram you got. Therefore, you got here joule and joule, H, capital S plus capital H, that will be the total H. So the confusing part I was talking about is here, when he tried to calculate H per unit mass. Okay, that is the mixture specific enthalpy or the mixture enthalpy per unit mass. The only trick here or the only confusing thing that I found when I was a student myself is that they don't divide over the mass of the mixture, they divide over the mass of the dry air. Fine, let's divide H over MA, this over MA, this over MA. And now you realize why they did this. So when they divide over MA, it cancels with each other. So this become HA over MA, so it become HA. And this one, you got M vapor over MA. What did we call this in the previous slide? Humidity ratio, right? So this will become our omega. So then when they want to calculate the mixture enthalpy per unit dry air, it's simply the enthalpy, specific enthalpy of the dry air plus omega H vapor, the joule, the kilogram water vapor, kilogram dry air multiplied by the enthalpy of the water vapor. All right. So it complicates our understanding what is the mixture specific enthalpy a little bit, but it makes our life much easier here because we said that this omega would be handy and we will have it in our hand just by knowing the phi. All right. So this is the mixture enthalpy per unit dry air. Okay. Now that H vapor. How do I get the enthalpy of water vapor? Steam table and what? Two properties, pressure and temperature, entropy and specific volume, entropy and temperature. Any two property, you go to the steam table, you should be able to calculate H vapor. But something that make our life easier, it may confuse a bunch of you, is that he would say that H vapor is almost like Hg. Okay, what is he talking about? So back over here, he's saying that the enthalpy over here is almost the enthalpy over there. Okay, so what he's saying? He's saying it's the same enthalpy at constant temperature. And if you remember, we did this very early in the course in this side. You remember we said that the vapor line were so close, the liquid pressure line, constant pressure line were so close to the key saturation, to the saturation line, and we end up saying that, well, if you have good steam table and you know the pressure and temperature, go ahead and get the enthalpy over here. But if you don't, just go to the next saturated state, go to the same temperature, and get the enthalpy HF at the same T, right? Even if you are here and you think this is what? Compressed liquid, right? No, go for the same temperature, but the HF, and we saw that it's pretty close. So on this side, and we are not really that high, we are usually low, right? Low temperature. He's saying that basically in this range, it's almost the same H. And this is faster when we calculate, because that line is available for us. We usually have good information about the saturation line. But over here, maybe we'll need to interpolate a lot, and maybe we don't have enough pressure value. So this is closer, and you will see that when we do the calculation, yes, that will include, it will cause a little bit of an error, but this part, all of it, this part is very little compared to this anyway. So the error is gonna be very minimum, all right? So, question you could ask right now, so you don't want us to calculate the H vapor based on the correct pressure and temperature? Well, if you have the steam table in front of you and it's handy, go for it. But in the exam, you may be running out of time and the table doesn't have enough information, and so this work. Okay, and again, you will see that the difference is going to be small. So now let's solve an example that basically